recording as well. So homework 1 is what folks have been working on, stopping by office hours to ask questions about. I wanted to point out some general resources for you that you have seen in our lecture materials thus far. My general philosophy is to make sure I've given you an example or template of everything I'm asking you to do in homework. I don't want you Googling or ChatGPTing. That is my job, to make sure that you're prepared to do the assignment. The idea behind the homeworks is to hopefully give you a way to go back over the material looking for something more purposive than just sort of the fire hose of information coming in, which is what I know it can feel like, especially with all of the notation and unfamiliar terminology. So first off, in lecture 3, if you don't remember how to get between correlations and covariances, here are some formulas for you. So in homework 1, some of the questions say like R, what's in the R matrix and what's in R core. If it's core at the end, that's the correlation version where you would have ones on the diagonal where the variances would be, and then the off diagonals are all correlations. If it's a V or R matrix, that's the variance covariance version where the variances are on the diagonal, covariances are on the off diagonal. So this should help with some of that. Also, all of the rules about maximum likelihood versus residual maximum likelihood in terms of what you can and can't do start in lecture 3 on slide 28. And I have this in a couple different forms. This table is probably the most direct in terms of describing what you can and can't do in terms of hypothesis testing. I also have it laid out in the very last slide here in terms of how the models differ from each other. So these are resources that go along with the text at the end of chapter 3 as well. Can I share the screen, please? Certainly. I was so close to being competent today. I could almost feel it.
You were also really intent on not letting us tell you that the screen wasn't sharing.
Yep. That's because I still had the recorder blocking your faces. That was the problem. But now we're good. Okay, but at least I'm narrating. So to catch up then, the slides that I pointed at in lecture 3, the very beginning, slide 3, describes how to go back and forth between covariances and correlations, if you need to be able to do that. And then the treatment of model comparisons when using maximum likelihood or residual maximum likelihood, that starts on slide 28-ish in lecture 3 and goes for the next couple slides. And so I'd recommend this table or the last piece here where it decides, labels what types of comparisons you can do. Okay, so that's what's in lecture 3 that should be helpful for your homework. Lecture 4 then, the ingredients to figuring out how to form things, like if I say element, 3, 1 in the R matrix or something, the ingredients are right here. So this is the variance covariance version of each of these matrices. So for instance, the AR1, if I asked you for cell 2, 1 of this matrix, and I gave you the R that goes into it, and I gave you the variance that goes into it. So if I asked for 2, 1 of R, this is the formula by which you would compute that. If I asked for 2, 1 of R core, then all you would need to do is just put the R part in and strip off the variance. Because it's R core is just in correlation metric, and that's directly what R is giving you. So this one will be relevant to you. Also relevant, I know for sure I have an autoregressive version. So there's one that has this one as well. So these are the ingredients of how you make each of the pieces here. And so for this one, I've given you the variance of the random intercepts, the variance of the residuals, and then the R parameter in the R matrix. So those are the places I would recommend revisiting to do the computations. Are there other questions I can answer right now? Not right now. Fair enough. So I looked at the database this morning. Most folks are not done yet, so don't be shy. If you need help, please ask for it. Just to make sure the recording is capturing this, this homework is not due until Wednesday night. Office hours today end at 3 o'clock instead of 3:30, but I do have regular office hours tomorrow from 3 to 4:30. All right, then we still have a little bit of lecture 4 and example 4 to get through, and then hopefully we can start in lecture 5, the more fun stuff. well, relatively speaking, the more fun stuff. Within topics centered, right? Sure. Hi.
Hi.
Happy Garbage Day, everybody. I feel like we're not quite awake yet. Yeah. Next week is your week off. I won't be here. I will likely have things for you to do, though, at a minimum, the formative assessment that is due the Monday after I return. I'd like, theoretically, to get your next homework up, but I'm not sure when that's going to be due yet. It'll depend on how far we get this week. We're a little bit behind relative to my initial schedule, so I'll have to figure out how to adjust accordingly. I may also, actually, I probably will have a video or two for you to watch as well. In particular, there's a part of lecture 5 and example 5 that deals with the connection between multi-level versions of these models and structural equation versions. I will put that as a lecture outside of class. That way the folks who haven't had SEM won't be like, what is she talking about? Because that's sort of a bonus advanced topic. But it's definitely something that we will return to in the advanced class more thoroughly in the spring. Okay, let me make sure I have example 4 open. That's the one document I'm missing. There we go. All right, I got to reorient myself. So how far back do we need to go? Should we start with the random intercept versions of these models? Would that be helpful? Maybe? We talked about this in formative assessment land last time. So the big difference, let's go with slide 19 to start with here. Let's go back a little bit. So there are two types of approaches for trying to structure what the pattern of person dependency is over time. Basically, what kinds of sources of correlation and heterogeneity of variance are induced by having the same occasions measured for a single person. That's the big picture. And there are options that use only the direct pattern. So R-only models, as I've been calling them. That's where they don't necessarily structure it into level 1 versus level 2. Compound symmetry is the only one that does. But they try to just build in patterns of correlation. So autoregressive is one, Toeplitz is one, moving average is another one that's been discussed in class, although I didn't include that in these materials. For the remainder of the semester, though, we're not going to have that approach. We're going to do this G and R combination approach. So G, let's do vocabulary, level 1 or level 2? Which one does G go with? I'll give you a hint. It's where the random effects live. 2. Yeah, so let's put it together. Level 2, between person, inter-individual differences. The U's, which are random effects, whose variances and covariances live in the G house. Okay? So G is going to be in charge of why do people differ from each other. Is it just in intercepts? Is it in their change over time? Is it in their effective time-varying predictors? All the ways that people could differ from each other systematically between persons. Then level 1 is within persons, intra-individual variability, time-varying, longitudinal, micro, and it has E residuals that live where? Which matrix or which house? Take your pick. What letter? R, yeah. So if it's an R-only model, then level 2 and level 1 are all stacked together. If it's a G and R model, then they're split apart into different places. But we put them back together again, and what is the put back together again marginal covariance matrix called? V! V for victory, we remember. Yes, or me, broken V. I'm double jointed. So. If I want to do V, I have to twist my shoulders to make my elbows cooperate. So stupid human tricks, as we used to call them on David Letterman. All right, so then the idea is that person differences are going to be the primary source of covariance over time. So why not take that as the biggest contributing factor, go stick it somewhere else, and then see what kind of pattern we have that's left over. Because that pattern can probably be approximated more parsimoniously than trying to structure the whole matrix at the same time. So then the choices, this is what a compound symmetry matrix would look like. This is slide 20 in a G and R pattern. So G is right here. That's one number so far. It's our random intercept variance. Wrapped around it is a matrix that we're going to call Z. This will show up in lecture 5 in more detail, but for now, all you need to hang on to, come on, see my monitor's blinking at me. All you need to hang on to is that the purpose of these ones right here is to blow this up so that it's the right 4x4 size to add it to R. Just hang on to that for right now, and we'll get into what they mean more specifically later. So in layman's terms, if you take this random intercept variance and just add it to every single spot in this matrix, this is what you end up with. So the pattern that's in V, when you put it back together again, is exactly the same thing as compound symmetry in R only. But this is going to allow us to add more stuff to G more readily. I can have a heterogeneous variance version as well, in which the residual variances per occasion could be different. That would require balanced time because there would be one variance per unique time occasion, whereas compound symmetry, this version, does not. Random intercept plus AR1. This one I like quite a bit. This one is very flexible, and I've seen it work well. It only has 3 parameters, so it's relatively parsimonious. What this one has is G, random intercept variance, R, residual variance, and then one autoregressive correlation that shows up in R only. So this is saying that the E's, the level 1 part, follow an autoregressive relationship specifically, not the total. You can put it back together again, though, and the variance over time is still this part U, part E, same number, homogeneous variance, but then the covariance has an extra component to it. So it starts with whatever is due to the random intercept, and then it adds to it an additional source of covariance based on the E correlations among the residuals here. So this basically says in English, yeah, people are different from each other. That's random intercept. So each person still gets their own mean over time. But then also occasions that are closer together are more related. That's a reasonable pattern. And at the end of this is where I added the 2 bonus slides to talk about the kinds of AR1s. This is the traditional kind right here that's built into software, where you do need to have equal interval occasions. And you can do a heterogeneous version of that as well. For Toeplitz, this is one where it's banded. So we have one variance on the diagonal of R, one off-diagonal covariance, a second off-diagonal covariance, and the last one has to be shut off in order for there to be room to have the random intercept. So this is saying that for the highest lag, the longest separation in time, the only source of covariance for that is just the random intercept. There's no extra piece. So this is one where we may not need all of the lags, and we can actually see how many we need. So here's an example of one lag only. So this one would say residuals that are 1 unit in time apart are still correlated, but after that, there's no more. So note the zeros here. This one is harder to find in software, particularly the heterogeneous version of it. And here is a chart that it took me probably 8 hours to make to try to figure this out, that describes how all of these things are nested within each other, as well as how many parameters they should each have. So these are just handy-dandy formulas you can readily use for your homework. This is in the book, figure 4.1. Built in PowerPoint originally, in case you're curious. I know, I don't bag on PowerPoint for pictures. It can work. The rest of this is just sort of words to keep in mind, cautionary tales and things like that. The part that I added is this right here. So this is an example of how to do continuous time autoregressive models, and I borrowed this out of the SAS documentation in particular. So these are the 2 slides I sent out on Thursday that are now appended to the end of lecture 4. So the way it works is it computes D as the distance in time between occasions I and J, and then it just sticks it in there. So if somebody had balanced data, then it would look like this, where you have lag 1, lag 2, lag 3, but then I and J could take on whatever values they need to be. So if you have occasions that are 1.5 in time apart, then the distance would be R to the 1.5 power. So it just sort of slides along like a continuous time vector to figure out exactly how far apart, what the correlation would be based on how far apart they are. So from what I understand, then I believe this model could accommodate unbalanced data as well as unequal intervals. Because this correlation is essentially customized by whatever exponent is needed as given by the time variable right here. So this is the SAS documentation for the repeated statement. I put a link to it so you can see all the other kinds as well as more documentation about that. In contrast, this is what I got for the R version. So that's it. Good luck. It's theoretically possible to make it happen, but it is not very well explained. But here's the manual where I stole these things from. But the type is core car1. In type, under the NLME package, the functions GLS or LME have that built in. So if you set it up this way, I believe you can have unbalanced time and unequal intervals. Stata does not have this as far as I could find. At least not in mixed. It might be in some other routine that I'm not as familiar with. Okay. In terms of seeing it work on data, example 4 here, so 7 weeks of weekly collection of psoriasis severity is the outcome. Up to the point, I think, where we had finished, the best fitting model was homogeneous topolets, but not by much. If I recall, it was like 0.06 something. Yeah. So relative to unstructured, as the answer key, as the model that will always have the smallest -2 log likelihood and the largest log likelihood, relative to that, this one is almost not worse because we have a significant likelihood ratio test comparing the two. So note, to your point earlier, this is all a conversation about the model for the variance. In all of these models, this is an empty means model because there's no systematic change over time and there's no predictors as part of the story just yet. So if we look at the random intercept and R models, GNR, as we call them, the answer key version is the same thing as unstructured R, but note the N-1, cough, cough, homework question. N-1 is because the last off diagonal is forced to 0 in order for us to have room to separately estimate a random intercept variance. You can't have everything be what it wants and then have one more parameter. That would be considered under-identified or overdrawn if you want to go with a bank account analogy. Spent more than you had. So the utility of this one, if you can find it in software, is that it shows you the answer key for the R matrix specifically, meaning just the level 1E part. What does that pattern look like? So the variances here are a little bit heterogeneous, not really in a pattern. Some weeks look different than others. The covariances seem to decline. If we look at the corresponding correlations, so this is the correlation version, it looks like there is some correlation for the first couple lags, but then it kind of dies off and becomes inconsistent. So my guess is that we might need residual correlation for like the first lag or the second maybe, but not past that. Okay, let me pause. How are we doing so far? Nods? Can we do a thumb scale? Thumbs are, the confidence interval of thumbs that I see is somewhere between so-so and up. Okay, any questions or things that I can say again or differently that might be helpful? Okay, I will just trudge on ahead then. So here's the compound symmetry version, random intercept in G plus a diagonal R matrix. So the two ingredients in that are the two that we're used to seeing. Variance of the random intercepts, variance of the residuals. They're just stored in different places. So R then, this is R code for the R matrix. The way that I got this is a function called getVarCove that works with the NLME package, and type equals conditional means the level 1 part. So there's marginal, that's V, put back together again. The level 1 part only is conditional. And so this is what a diagonal R matrix would look like. It has residual variance of the level 1 E's on the diagonal and zeros everywhere else. If you take that and stick the random intercept variance in every spot, then you come up with the marginal covariance matrix, which is V. The put back together again version. That's what marginal means in this context. And this correlation, this matrix, excuse me, can be used to compute an ICC. So to convert the random intercept variances and residual variances into an interclass correlation. And unfortunately, in the LME package, there is no ICC function. I know, I'm like, seriously? No one has asked for this? So I built it. And when I say I mean Jonathan. Because I'm still not very good at getting things out of matrices, but this worked. What? I'm being honest. I have made some tremendous improvements in terms of getting Stata to remember numbers and do computations, and I'm getting better at it in R, but I'm still not good at it. I would say I am less shitty than I was before. But we have not yet crossed like the 0 point of the number line of skill for me. I'm still on the negative side. But there, we can get an interclass correlation by using the objects and computing it ourselves. Let's see, I had to re-estimate the unstructured model using GLS in order to do a likelihood ratio test, and it is decidedly worse. So same thing that we found earlier. If we look at the autoregressive R version, so that happens in SAS by adding AR parenthesis 1 to the repeated line. It happens in Stata by adding AR1 to the residual section. And right here, there used to be a no constant that's gone. Now the intercept is there by default. And in R, it happens with core AR1. That's the non-continuous time version, the standard version. So in terms of the pieces that you get out of this model, there's 3. And I have these labeled in the SAS output because they're not directly given in all the programs. So the first one is your variance of the random intercepts. That's what G has, between person mean differences. The AR1 term is the R correlation that goes in the R matrix. That controls how correlated your E level 1 residuals are, and that gets squared if it is 2 occasions apart, cubed if it's 3 occasions apart, fourthed if it's 4, and so on. And then residual is the E variance now specifically. So that's the variance of the E that remains at each occasion after factoring out the random intercept and sticking it over in the G matrix. So 3 terms. In terms of comparing it to the right answer, still worse, but we're heading in the right direction. And I have a note here, cough, cough, homework question. If I'm comparing the random intercept plus AR1 model to AR1 only, if the random intercept helps, that means it's not the total pattern that's autoregressive. It's only the residual part. Otherwise, the random intercept would not have helped. In terms of the pattern that is being built, so here's the Stata output. That's my random intercept variance. I have these labeled out here. Then I have rho as the autocorrelation, and then var E is the residual variance of the level 1 E's. Here's the pattern that it builds. So this is the R matrix. On the diagonal are the variances of the E's at each occasion. The off diagonal are the covariances that were created from the autoregressive correlation and these variances. So I asked for that next. This is the R matrix that gets created. So the autocorrelation parameter was estimated at 0.51. That's lag 1 E correlation. If I square that, that's lag 2 E correlation down to 0.26, and so on. So you can see that it dies off to almost 0. A correlation of 0.02 is what is predicted between the first and last occasions. V matrix, though, right below it, this still has a lot more covariance in it because of the random intercept. So putting the random intercept back in says there's an additional constant source of correlation beyond the autocorrelation that is customized to which particular 2 occasions. And to do the model comparison, I had to re-estimate the AR1. So there's the model comparison in R. And this one is still technically worse than the unstructured model, so we could keep going. I did the Toeplitz version to see what it looked like under that. It gives me random intercept variance plus all of these residual covariances. The correlation version looks like this. So once again, it appears that after controlling for the random intercept, there's not a lot left in the R matrix. Correlation's around 0.5, 0.2. So then the question is, how many of these off-diagonal bands would we need? Well, eyeballing it, I'm going to say this one for sure. That looks like it's enough of a relationship to need. Maybe this one. After that, So I decided to skip some steps and do all the comparisons here. So there's the summary of taking them out one by one. Question?
Can we go back quickly to the last Toeplitz slide? Because
Sure.
there's a negative correlation. What does that even mean? How do you interpret that?
It means that it decided that this should be a negative correlation, or a negative covariance, actually. It's estimated in terms of covariance and then turned into a correlation. I would say it's just sampling fluctuation around 0 is what I would say. Where the data that it's trying to approximate are in, let me go back up here, the unstructured model. One more model. There it is. So these are the covariances that were estimated directly when you let everything be what it wants, and these are the correlations, and they are indeed negative. So it's essentially trying to come up with like an average of these three to figure out what that would be, and then an average of these two. So, yep. Noise is what I would call that. Like theoretically, it's possible that they're negatively correlated, but I wouldn't expect that a lot of the time. Okay.
And
Yeah,
just
go ahead.
to make sure I'm interpreting that correctly, a negative correlation in this place in the matrix would mean as the time gets farther apart, they get more related to each other.
No, it would mean like if you are above your line at like a time 1, then you're likely to be below your line at time 7.
Okay, thank you.
So that could make sense if it were a compensatory thing,
Okay.
like you're bouncing around some kind of equilibrium.
Okay.
Sure, we'll go with that. Okay, so then Toeplitz story summarized very briefly. It looks like if I take all of them out systematically, so 4 lagged relationships, these are the fit statistics, this is out of SAS, 3 and 2. It looks like 2 is too few, 4 is unnecessary, 3 lags is where I landed. So then I estimated that model in SAS and in Stata, because R doesn't have it. So this is what it ended up being. So lag 1 covariance, lag 2 covariance, lag 3 covariance, and then the blank spots are zeros.
Sorry, I have another question.
Please.
So for the taupe and then the number, wait, are we looking at random intercept plus or without? Because I thought if it says like Toeplitz 3, then that means there's 2 lags because we're also counting the variance.
Yes. So this one depends on your software. SAS calls this taupe 4. Stata calls it taupe 3
Okay.
because Stata does not count the variance on the diagonal and SAS does. But the pattern is right here. So if we start with R, this is the variance covariance matrix of level 1 residuals specifically. If we take that and stick a random intercept variance in every single spot, that gets us to the V matrix put back together again. So there is a covariance expected at these blank cells, but it's due only to the random intercept variance. There's no extra residual relationship built into this pattern. And so that shows up in the same way in the correlation version. And then one more question, do they need to be heterogeneous variances? And if that happens, then the covariances change to correlations. So those get to be constrained. So these are correlations instead of covariances. And then it's built like this with different variances on the diagonal. And that one, survey says, in terms of likelihood ratio test, is better than the homogeneous version of this model and not worse than the heterogeneous version, or the unstructured version. And normally I have a results section that I give you at the end of my examples, right? This is it, this paragraph. Because no one would care. Like 19 pages later, no one's going to want to read this. So here's my summary. To maximize power, we sought to reduce the number of parameters. We found a model that did so. I win, and that's what we used. Boom. That's all I would say. Yeah. And if reviewer 3 wants more information, then this could become some kind of supplemental appendix type thing. So I've taken to including additional analytic details and results in appendices. That way the reviewers can see them if they care and not if they don't. So homework 1 is the only homework you're going to have on this topic. After that, we're switching gears and moving into random intercept and slope models for the next 2 months. And then predictors. All right. Questions on any of this? All right, can we say goodbye? We'll wave goodbye to example 4, lecture 4, lecture 3 for that matter too. Yeah, bye-bye. There. If there's anything that I went over too quickly and you have questions about it, please let me know.